How does chain entanglement affect polymer properties? Imagine a busy ball of yarn where each thread twists and turns around others, forming a tangled web. That's similar to what happens inside a polymer material. When long polymer chains intertwine and cross over each other, they create what we call chain entanglement. This physical interlocking is key to understanding how polymers behave under different conditions. Chain entanglement restricts how easily individual polymer chains can move past each other. Think of it like trying to slide a tangled rope. It's much harder than sliding a loose one. This restriction makes the material stronger and tougher because the chains share the load when stress is applied. When you stretch a polymer with many entanglements, it resists breaking longer, showing increased strength and resistance to deformation. That's why some plastics can stretch without snapping immediately. But if the chains are too tangled, the material can become brittle. Imagine a very tightly wound rubber band that snaps easily because it cannot stretch further. High entanglement density can also make processing more difficult. When melting polymers for molding or extrusion, more entanglements mean higher melt viscosity. It takes more energy to flow the material, which can slow down manufacturing or increase costs. Entanglement also influences how polymers crystallize. Crystals form when polymer chains align in an ordered way. If chains are too tangled, it can prevent proper crystal formation, affecting the final strength and flexibility of the product. Sometimes, slower crystallization results in fewer entanglements, which can make the material less tough. On a microscopic level, scientists describe entangled chains using the reptation model. This idea suggests each chain moves within a virtual tube created by surrounding chains. Movement is mainly along the chain's length, which affects how the polymer relaxes after deformation. When chains are highly entangled, they take longer to relax, impacting how the material responds to stress over time. Controlling chain entanglement is essential for designing polymers with specific properties. By changing the molecular weight or adding other materials, manufacturers can adjust how tangled the chains are. For example, reducing entanglements in thin films can prevent brittleness, while maintaining enough in bulk materials ensures durability. Understanding chain entanglement helps explain why some polymers fail prematurely or how they can be made more resistant to mechanical breakdowns. If there aren't enough entanglements, stress can cause chains to slip and break, leading to failure. Too many and internal stresses can develop, weakening the material. So, knowing how entanglements work allows scientists and engineers to create better, more reliable polymer products.